Hello, and welcome back to Aggressive Physics. Today is day 29, where we're going to explore vectors in equilibrium. And what I'd like to do first is revisit our discussion of vectors from before. And remember, a vector is something that has variables and magnitude as well as direction. So it's a number with a unit, and it has a direction associated to it. So for example, velocity was a vector that we used. Velocity had a number, like 50 meters per second, and it had a direction, east. So 50 meters per second east is a velocity vector. On the other hand, we could have wind velocity. And the example I have here is 10 knots south-southeast. The 10 knots is a unit of measurement for wind speed. And the east-southeast is going to represent the direction of the wind. And what's strange about wind is always listed as where it's coming from, not where it's going to. So east-southeast means it's going from east-southeast towards the west-northwest. So wind is a little strange in that aspect. That being said, on the other hand, we have scalar quantities. And a scalar quantity is a variable that just has magnitude. So it's just a number and a unit, and it doesn't tell me what direction it points. So for example, 55 miles per hour would be our speed. Speed is a scalar, and velocity was a vector because it had direction associated to it. Some examples of vectors versus scalars are given on this slide. And we have weight and velocity and displacement and force as examples for vectors. Force is something we're going to cover a little later. We've discussed weight already, velocity, and displacement. On the other hand, we have scalar quantities. Scalar quantities such as mass and speed and distance, length, width, and height, temperature. Those are all examples of scalar quantities. And sometimes assessments will ask simply which one of these set of four is an example of a vector, or which of these set of four is an example of a scalar. But watch out for the trick questions where in bold they may have not a scalar or not a vector. And in that case, the first answer may be a vector, but you have to find the one that is not a vector or not a scalar. So just be aware of the way that questions are asked on assessments and answer the actual question that they're asking. What a lot of students find is that they get problems wrong because they don't read the question in its entirety. So make sure you do that. I've even used highlighters or underlining the key words in order to make sure that I'm answering the right question. It's easy to get tricked by physics questions because there's so much information we cover and there's so many different ways to solve problems that we'll often overlook the simple things like actually reading the problem and understanding the key words that are in the problem. That being said, this is not an all-inclusive list. We have many other scalars and vectors that could come up, and as we move throughout the course, we're going to talk about more vectors and scalars as we continue. Another example that's not on the list of a scalar would be time. We never use direction when dealing with time. It's just a scalar quantity. Now, if we take two scalars and multiply them together, we end up with a scalar. If we don't start with a direction, we don't end with a direction. If we take a vector and multiply it by a scalar, we stay with the vector. Examples of equations that dealt with that were the v equals d over t. Velocity is displacement over time. In that case, instead of multiplying, we are dividing, but we end up keeping the unit when we only have a single direction in the equation. Now, there is a situation where we can multiply two vectors, and that's going to be something you would cover in a higher level math course or a higher level physics course. And what you end up getting is typically a cross product, and there are different rules dealing with multiplying two vectors together. That's something, like I said, that you'd cover in a higher course, but don't think that I'm not including that possibility. It's just something that's not within the scope of this course. Typically, we're going to start with two scalars multiplied together. You've been doing that forever. In any class, you've multiplied two numbers with units. In addition, this course we've added multiplying a vector by a scalar. and that way you keep the vector, and you basically have the same direction that you started with. In the future, you may deal with more complex problems, and you have cross products. In that case, like I said, there are rules that govern the different scenarios that occur within that scope of mathematics as well. Now, that being said, just two of the examples, and we've discussed this before, I just want to reiterate it here. Displacement is your location from where you started to where you ended. It's the difference between your start point and your end point, and it has a direction associated to it. If I start at the origin and I go 3 paces east, my displacement would be 3 places east. If I start in a specific spot and I go in a circular pattern and I end up back where I started, my displacement would be 0. On the other hand, the distance is how far you've traveled in its entirety. So if I were to go 3 paces east and 3 paces west and then 3 more paces west, my displacement would be 3 paces west. My distance, however, would be 3 plus 3 plus 3, or 9 paces. So I could have 2 different answers based on the fact that I'm asking 2 different variables. If I ask for the distance, it's how far total. If I ask for the displacement, it's just how far I end up from where I started. Now, in a circle, I may tell you that I've traveled in a circular path and my displacement is 0, but the distance I've traveled is the outside of the circle, which you know from math class is called the circumference. So you may have to find the circumference by giving possibly the radius or the diameter. And remember that circumference is 2 pi r or pi d. So you may have to use some of your math that you've learned in geometry. Now don't worry, the equations for the circumference and area of a circle are listed on the reference table. So you look in the geometry and trigonometry section of the reference table and you'll find it there. Now, how are we going to denote what a vector is versus a scalar? And if you recall, we use the half arrow symbol. Now, a lot of times we get lazy when we're dealing with the vector equations. If we were dealing with many equations like we've done, we typically ignore the half arrow on top of the variables. We're more concerned with getting the answers correct than worrying about all the proper notations. But if you're dealing with the examination or an assessment, you'll want to put the half arrow symbol over the vectors, and you just won't put a symbol at all over variables that are scalars. For example, the v, if you're dealing with v itself, it could be velocity or speed. If you have the half arrow, it represents velocity. If you don't have the half arrow, it represents speed. If you have a textbook, they'll often use boldface type to represent the vectors and standard type to represent scalars. If you were writing a lab and you were typing it out, you can use the same notation. You can use the boldface type to represent vectors and standard type to represent scalars. But if you're doing it by hand, a half arrow will suffice. Now, in this chapter, what's important for us to do is start to use a graphical approach to solving vector problems. One of the things that is often asked on Regents examinations or assessments is drawing the resultant of a couple of vectors. And they're not always going to be right angles where you would opt to use trig to find the displacement. Instead, they may be at strange angles, 30 degrees north of east and 70 degrees south of west, and different angles like that, and you'll have to deal with the typical angles that are non-right. In that case, there are ways to solve that mathematically using law of cosines. We're going to have a method here that's going to simplify that process and allow us to solve any vector mathematically. However, we're going to start with a graphical approach. And what we're going to need is a couple of things in order to represent the vectors. First, we're going to need some mathematical tools. We're going to need some equipment in this case. And the equipment is going to be a ruler and a protractor. The ruler should be metric, so you should have centimeters on one side. You can use a 12-inch ruler that has inches on one side and the metric system on the other, typically centimeters. You may also have a completely metric meter stick, or you could have a 6-inch ruler and centimeters as well. The other thing will be a protractor. I typically would like a protractor that is generally small so that the lines are going to be long enough for me to read the values, but you could have a protractor that's a little larger. You may have to expand the lines in order to measure the angles if they don't reach the edge of the protractor. But for this section, you're going to need a protractor and ruler in order to solve vectors graphically. Now, the things we'll need to do once we have our equipment is set a scale and then have a coordinate system. Then we'll draw the vector to scale in the direction that our coordinate system is set up to be in. Typically, our coordinate systems will be the XY coordinate system, or if we're doing a problem that has a real set of vectors, we'll use a map typically, and that will be the compass. It'll be north, south, east, and west. So our two coordinate systems, the coordinate axes, if you will typically be X and Y, or north, south, east, and west. Now, when we're drawing a one-dimensional vector, we're going to start with 1D vectors and then move to 2D vectors. What we're going to have is a procedure. And the procedure for now is something you should write down, you should follow so you can click through and make sure that you have each step. But ultimately, this will be something that will become second nature to you. What you'll do is define a reference line. Then we're going to set a scale. Typically, 1 centimeter equals whatever the unit is that you have. You want to make sure the scale is appropriate for the page you're using. You want to fill up the page as big as possible. If you're using a whiteboard, you're going to want to make it as big as possible within the confines of the whiteboard. If you're using a standard piece of letter paper, you'd want to have a scale that fills up the page as much as possible. And there's a reason for this. It's because then if you make any mistakes, and let's say you draw a vector a little too short, any mistake you made will not be amplified. The smaller the vector, the bigger the mistake will be amplified. The larger the vector, the more room you have for error. And you want to minimize your error. You're never going to be able to eliminate it completely, but you want to minimize error as much as possible. That being said, once we have an appropriate scale, we're going to draw our vector in the proper direction. I will often have a dot representing the origin. I'll draw my line in the direction that I'm going toward, and I will draw an arrowhead at the end. And it's important to draw the arrowhead so the tip of the arrowhead is at the end of the line. You don't want to start an arrowhead at the end of the line, because then that will make the line longer than you measured. So you want to make sure that the end of the arrowhead, the tip of the arrowhead, goes all the way to the end of the line that you drew. So if you draw a 7 centimeter line, you want the arrowhead to end at the 7 centimeters, not begin at the 7 centimeters, because otherwise you're going to make it longer than 7 centimeters. That being said, what I think we should do at this point is a couple of example problems. I'll start with one together, and then I'll ask you to draw a few on your own, and then I'll draw them to verify that you did them correctly. The best way to get better at physics is by practice, and in this case we're going to do a number of practice problems, some together and some separately, so you get better at drawing vectors. And that's how you draw a vector. You basically set a scale, you have a coordinate system, and you draw the vector in the direction of the coordinate system. If you're dealing with one dimensions, it will typically be east or west, north or south, left or right, up or down, positive or negative, something to that effect. It'll typically be along an axis, and it will be fairly easy to draw the vector along that direction. But you need to set what the coordinate axis happens to be. Once you do that, you draw your vector, put an arrow on it, and then I will label my vectors, because we're not going to be just drawing a single vector. We're going to be drawing multiple vectors for a problem, and it's going to be important for you to label them so you know what vectors you've drawn already and what vectors are still to come. So that's how you draw a vector, and that's our discussion for today. Let's try some practice problems now. For the vectors section, what I decided to do is switch over to a pen. Using the dry erase markers, I'm constantly marking over previous lines. I'm rubbing it off my hands, and that's fine when the problems have a continuous structure to them. Typically, I'm able to start on one side, work my way down the page, then I work on the other side. With vectors, because we're going to be constantly going back and forth over lines that we already drew, what that's going to do is cause a situation where I'll constantly knock the lines off if I'm using my dry erase markers. So I'm going to try to go with a pen. Hopefully it's dark enough to see. I have a ruler here, and I just marked off the inches so that we don't get confused. All that are visible here are the centimeter side, and then I have a protractor as well. So when we're drawing vector problems, what we want to do is start with the vector. And I have vector 1, I'm going to call it V1, and that's going to equal 50 meters west. 50 meters west. And what we're going to do is define our reference axis, which in this case would be east and west. I'll set a scale. 1 centimeter equals, I'm going to do, I'll just do 5 meters. And if I need to convert, I could do that conversion. I would do 50 meters. And if I want to convert to centimeters, 5 meters on the bottom, 1 centimeter on the top. I use this conversion factor for this problem. And my line is going to be 50 divided by 5, or 10 centimeters long. Now, for this one, I probably don't need to do that, but that's how you would do that if it's a strange conversion that you're faced with. You would, in this case, start with a dot. We're going to go to the west 10 centimeters. So I'm going to hold my ruler so that I line up the dot with the 10. And I'm going to move my way to the left. Oop, slid a little bit. Do it again. All the way to the 0 point. Now you're going to want to be on top of the line, and the 0 point is where I'm going to draw my arrowhead. I start at the 10 and I draw my arrowhead backwards so that I don't get confused or do the following. If I were to start like this, here's my line, and then I start my arrowhead here, and this is obviously exaggerated, but what I just did is added an entire, what is this, about 2 centimeters to the line. So that would throw off my result. So we don't want to do this at all. We want to avoid this type of process and just draw the arrowhead at the end. Now finally, what I would want to do is label it V1, put my half arrow because we're in the vector section, and that's how you draw a single vector that's represented by a single coordinate axis, in this case east and west. What we'll do now is a couple of practice problems that show more samples in one direction. All right, we have 4 practice problems here, A, B, C, and D, and those are listed in the packet. And what you're going to be able to do is each one is a separate problem. So all I decided to do is make 4 squares in my paper. I folded it twice, and we have 4 boxes to work with. Each one of these is going to require a number system. So for the first one, plus and minus, I'm going to do plus and minus. I'm going to say 1 centimeter equals 5 miles per hour. And I noticed that the pen wasn't really dark enough, so I'm switching over to a marker, permanent marker. Hopefully that will eliminate the problems of me erasing the lines as I move my hand over it. My left-handed curse. In this case, if we're going positive, I'm going to need to draw a 10 centimeter line to the right. So I'm going to take my ruler. I'm going to draw the line to the right. Oh, and I went over into the other box, but that's not the end of the world. I have A going that way. There would be vector A. Vector B is 10 meters to the west, so I have the east-west coordinate system. East to the right, west to the left. 1 centimeter, I'm going to do 1 meter. And I'm going to draw a 10 centimeter line to the left. That being said, I am going to put a dot at 10 right here. Show where I start. And I'm going to go to the left. Oop, just about there. Arrowhead, label B. Make sure when you're doing this, you want to measure diligently. You want to be measuring on top of the lines. You don't want to look to the side like I'm forced to do here as I'm recording. Now 75 newtons up, I would have up and down like that. I would probably do 1 centimeter equals 5 newtons. Now you may be asking, what's a newton? A newton is a unit of force in the metric system. Unit of force in the English system would be pounds, and this is a conversion that represents kilograms versus what we typically use in the English system, which is slugs for mass. But ultimately, you take the mass and you multiply by 9.8, and you'll get the number of newtons that an object has in terms of the force of gravity on it. And that's a little foreshadowing for our next chapter. Now, in this case, I'm going to have to draw a line that is, let's see, 75 newtons. And 5 newtons is 1 centimeter. What's 75 divided by 5? Isn't it 15? 75 divided by 5. Look at that, it is. So I'm going to have to draw a line 15 centimeters up. And unfortunately, this is going to be bigger than the box. I'm going to draw it over here just so that I can avoid most of what I've already written. I'm going to go all the way up to that end of this centimeter ruler, draw my arrowhead, and then list C as my value. So C is the label I'm going to use for the vector, and that's vector C. And then finally, vector D, we're going to go to the northwest. So the problem is we have north, south, east, and west, and we haven't talked yet about two-dimensional vectors. So how would we handle this? What I'm thinking the easiest way is to just realize that northwest is in this direction, and what's the opposite vector in terms of a single dimension? Well, if it's northwest and southeast. So what I'll do is I'll just draw a line like this to represent northwest and southeast. Now that being said, I'm going to have to set a scale. 1 centimeter equals 15 miles per hour. And I'll have a 10 centimeter line going up at an angle. And I'll start at the origin. And I'll do a 10 centimeter line. Now I didn't measure any angles, but I'm going to point it in the direction of my reference axis that I drew, and I'll label it D. Now there's got to be a better way to do this. And once again, this is our foreshadowing to our next topic, which is going to be how do we draw two-dimensional vectors? And let's see how we do that next. The reality is this needs to have an angle, and we got to talk about what that angle is.